Hi folks, in this video I will be performing modal analysis of a two-story shear frame structure. We'll be using beam elements and assume that the floors are rigid for simplicity, rigid structures for simplicity. Now this is in the playlist that I'm preparing for some modal analysis of frame structures which are available and done in the ABAQUS CAE. This particular video is the 3D experience counterpart of what the YouTuber below has done for the ABAQUS CAE. Now, the actual three-dimensional frame structure is assumed to be a series of these 15 feet apart, and this 15 feet comes into the picture by calculating tributary areas. So that is all done in the reference below, and you can consult that. It is assumed that the type of the sections are different. They're wide flange beams, but because we are assuming that the horizontal beams, first and second floor, are actually rigid, the actual cross section does not come into the picture except for calculating the weight and the mass of these things. But in order to do it with finite elements, you have to mesh these rigid areas, and we're going to use, for example, the same cross section that is used for the columns that they're mounted on. Okay, so for example, the top one is going to be using the same cross section as the two columns right below it, and the first floor beam is going to be using the same cross section as the ones that are mounted on. However, that cross section does not come into the picture when doing the FEA simulation because these are rigid. This is going to be rigid. Now, this particular problem actually is done is from the Mario Pazza structural dynamics problem, and one can consult there too. So this is a redrawn situation. These are the actual cross sections shown, and we are assuming that the structure is made out of steel. So the calculation using tributary area, etc., gives you the mass of the first floor, 136 inches, slinches. This is weird unit for in the imperial system for mass, and then M2 is 66. Young's modulus and Poisson ratio are given here, and the density of steel, which is only used for hand calculation of M1 and M2, this is the actual value. However, because the columns are assumed to be not contributing to the natural frequencies, when it's modeled as a multi-degree of freedom system, we will assume that the density of the structure is zero. However, when you do that, you get an error message, okay? And the YouTuber who's done it in CAE also alludes to the same thing. It's just like in 3DEXPERIENCE, you not only get a warning, but it won't let you do that. So this is why I will go and change the density to something which is a lot smaller than the density of the steel, and that guarantees that it will not actually contribute to the calculation. Now, the details of the cross-sectional areas for these wide flange sections are given there. And I want to point out to something, and that is what you see on the left side is actually the information that you have to type in based on the table that I showed you in the previous slide. Because we're dealing with the beams of non-circular shape, then the local coordinate system of this beam is extremely important. And when you look at it closely, there are three axis system. This actually is a mistake. That should be this should be a one. This red arrow should be the one coordinate system. You can see that axis system one, axis one is the red one, etc. That's a typo. And now in the YouTube reference below, the diagram looks like that. For me, it's going to be looking like this. And notice that they are kind of in the same direction. And the one on the left is the section properties definition dialog box from ABAQUS, and the one on the right is the section properties definition for the 3D experience. That should not surprise you because the solver in 3D experience is actually the ABAQUS program. And by the same token, this is going to be the other beam section. And now we're going to be defining the we're going to declare. You'll see that we're going to declare this top floor and the bottom floor as rigid entities, and rigid entities have a reference point, and we place the mass of the top and the bottom floors in that locations, that reference point. Incidentally, that is essentially tutorial 2 that I have done for a simplified version of this, which is one-story shear frame. You may want to look at that. Here, we have to, because we're not merging the nodes or we're not joining the structure, as I've done in tutorial 1 and tutorial 2, I have to tie these nodes. For example, for the first, for the don't worry about this arrow here with the highlighted yellow area. We'll come to that in a minute. So for the first floor, the rigid, the main or primary surface or wireframe is that horizontal section, and the 4 vertical columns are actually the secondary section associated with this rigid floor. And when you do this and you run it, you will see that you get an error message because it turns out that you have to go and activate this thing and put a number that is not 0. Okay. When you use 0, it's going to bomb out. Okay. So we'll come to that later on. And frankly speaking, when you try to come up with the error message, decipher the error message that it gives you, it tells you something about position tolerance, etc. And this is what's coming in the help document for the experience / ABAQUS, and it's not very useful. Okay, because mainly it's written for surfaces, and we don't have surfaces here. But anyway, just left that here for you to see. Now, for the second floor, the main structure is that horizontal beam on the top, and the secondary ones are these columns that you see here, these 2 columns. Okay, and once again, if you don't specify this to be 0, you get some weird error message, and you can't proceed any further. Okay, so I have to go and check this and put a tolerance which is small, and you'll see that it runs in that case. Now, that issue did not occur in the YouTube reference that I'm talking about, because this particular checkbox is not even available in the when you do beam problems in the ABAQUS. Here is the actual full page about defining ties, and this is what I showed you earlier, and it's not very helpful. Now, the YouTube reference gives you these frequencies. The first 2 are due to rigid body modes. You might as well ignore it. But the ones that we want is these latter 4 values. And that is what comes out of the 3D experience. And notice that 1.82, 1.77, 5.22, 5.093, etc. So they're very close to each other. Okay, so let's go ahead and do that. We're going to go to the 3D experiences interface. I'll change the name of this so that I can find it in future properties. I'll call this thing tutorial 6, tutorial 5. Okay, and say okay. Immediately save. I have already changed my units so that the units are in inches. Let me remind you how you do that. You go to preferences, and under this application preference, actually at the common preferences, select the units item, and then you can change your dimensions based on this pull down menu. But I have selected the imperial units. Okay, so okay. All right. Now, what I'm going to do is I will create, let's see now, 1, 2, 3, 4, 5, 6 nodes, which represent 6 points, which actually are these junctures, and then a seventh node for defining orientation. Okay, so of course, these dimensions are going to come into the picture when I try to create the points, and you have it. So let's go ahead and do that. Let me go to the points. And I start typing in. So this is the first point. The next one is going to be 180 inches up. 180 inches up. Let me fit this thing so that you can see it better. There we are. The next one is further up, which is 300. 180 plus 120. The next one is going to be to the right, for example. Let me do the ones, so that's going to be 450 in the Y direction. In the Y direction, 450. There we are. And then come down to 180. Okay. And finally come down to 0. Okay, so I've created the 6 points for the beam, and the fourth one or the seventh one I'm gonna use for reaction, orientation. And I'll use a negative x in this direction, for example, minus 100. Now you can use plus. It's just that those coordinate system, axis 1, axis 2, axis 3 will be different from the one that's in ABAQUS, but it doesn't matter. In the first 4 tutorials for the orientation point, I use positive value, which is on this side, but here it's going to be on that side. Cancel. So there we are. Now, let's create our beams or beam structures. So we go under Essentials, double click on line. So we go from this point to that point. Then go from here to here. Let me do on this side, this one to that one. This is the right column, and this is the second floor right column. And now we're going to do the beams. One go from here to here. The order of these things is not important. All right, and one from here to here. Good. And when you're done, you just cancel. That's your essentially your geometry. Now, while we are at it, let's apply material to this thing. So we go to tools. And there is a material. I'm going to create a material. Today is February 8th, 2024. And let's call this thing steel. And then we're going to say OK. When it's generated, I'm going to select it. Refresh this. Going right there. So I say apply. I'm going to close this and apply to that. Check the green box. And then we're going to put in our numbers. Double click. Okay, so structural density. Now remember, density, I already changed my unit, but I said that if you put a 0 here, it's going to come back with an error message. I'm not going to do that, so I'll just change it to whatever I said, which I believe it was a dummy density of 0.001. It doesn't matter because we're going to assume that the mass of the columns are negligible. That's why we have a small density. And the top and the first, second and first floor are actually rigid entities. Okay, so that's this. Oops. So now we're going to go to ABAQUS Multiphysics, Mechanical, Elasticity, Elastic. And this thing is 30 million. PSI, 1, 2, 3, 4, 5, 6, and Poisson ratio is 0.3. And then we say, okay, and that takes care of the proper material. Now, we are done with the model, so let me do a quick save here. Now I'm going to go to the measure, which is structural model creation. It's an empty FEM. Okay. So we go under the meshing tab right there, and there's the beam element. You click on it. Let me remind you that in tutorial 1, I created this the structure as a 2D sketch, and then I joined it. When I join it, then at the juncture you have, and you mesh it at the junction, you have unique node. Okay. In tutorial 2, I did not actually join it. I drew this thing as wireframe, just like I did here. However, I checked this box, which said that if there are two nodes that are within a tolerance of each other, then merge them. That was tutorial 2. And in tutorial 3, I did exactly what I'm doing here, except that it was a one-story build. Okay, so I'm not going to do that. The size of the element is 9 inches. And notice that here I have an option of linear element and parabolic element. Now, the reference that I'm referring to, YouTube reference, uses parabolic element, but it's two-dimensional, of course. I don't have two-dimensional elements in 3D experience. We don't have it, but we do have a quadratic one, three-dimensional. And later on, we're going to turn it basically into a two-dimensional by preventing the motion in the X direction. So we are using B32, which is right here, okay? And the size of the element is there. And let's start doing on the left side, this one, mesh it, say okay. Do another one, that fellow, mesh it, say okay. Another one, I'm doing the columns right now, mesh it, okay. The second floor column, on the right side, mesh it, okay. Now we do the horizontal beam, so this one, mesh it, okay. And finally the top one. Now remember, although we are meshing it, you don't really need it, but if you're using rigid element, you have to mesh it, and you have to have properties associated with it, as you'll see later on, and mesh it. And we say, okay, now, let me convince you that actually we have a problem. So if I right click here and say visibility manager, and say, okay, don't show me the part. I don't want to see the part. So there we are. These are the elements based on the size that I use. Now, if I say, okay, show me display, look at what happens. Display the numbering visualization. It says, well, you have to first update. Say, okay. So update is right here. You click on it. Now you click on numbering visualization. And if you zoom in, for example, to this top location, and if you put your cursor on it, it shows you a node number. Actually, it's kind of hard to see. So let me change my background color to something else. So right click ambiance to blue design. And now when I put the cursor here, it says node 238. If I go from this side, node 43. So these are different nodes that have to be tied together. You don't have that issue as if you did it like in tutorial 1 or tutorial 2, but you will have it here, which is essentially tutorial 3, but a more elaborate version of it. So that's good. Now, I'll leave this thing as colored blue, doesn't matter really. Okay, so it's already meshed. Now we're going to create profiles. We have to give it the cross-sectional properties, but to do that, you go to properties. First, you define two profiles. One of them is W1022, the other one is W1045. So you click on it. Let me call this thing W10 by 22. This is just a name, and it's going to be I. This table pops up, and then you just have to type in the numbers that I had in the slides earlier. So let me do that here. And so to start here, first one is, let's see for a second, 5 point something. Yeah, 5.085. 5.085. This information is in the slide that I gave you, and you can find it in any strength of material books, basically, on different wide flange beams. So 1017, the units are in inches. These are all in inches. 1017. This fellow is the B 5.75. And notice that as I put these things, oops, wait a minute, that's not right. 5.75. And notice that as I put these things in, these icons on the right side, they begin to light up. I mean, actually, it tells you what this thing is. This, like this one, is also 5.75. Next one is T1. T1 is over here, and that is going to be 0.36. Next one is also 0.36. And the last one is, I believe, 0.24. Yep, 0.24. And I say, okay. Now I do another one, and this one I'm going to call W10 by 45, and the cross section is again I beam. So let's put our numbers in there. That's also in the slide. 5.05. 5.05. Next value is 10.1. Next value is 8.02. B2 is 8.02. T1 is 0.62. Next one is also 0.62. And the last one is 0.35. 35. And we say, okay. All right. So we have created our profiles, as you can see here. And now we're going to do the sections. So we go to the beam section. Notice that I have my orientation point hidden. So if I go either get it from the tree, or if you click on in the visibility manager, click on the eye, it comes back. So there's my orientation point. All right, let's start doing this thing from left to right. So this fellow, that fellow, that guy, this guy. Oh no, sorry, I made a mistake here. Not this. Not yeah. These three are 1045. Now the horizontal one, I used it, but remember, this is a dummy one that has to be, it has to be specified. However, actually it's not used in the calculation. Okay, so so these three, and then we want profile 1045, and the orientation point is that point. Okay, and then we say okay. Now we do the same thing. So one of them is created. Let's do the other one. So another one over here. So it's going to be this fellow, that guy, and that guy. And this is 1022. The orientation point is once again the same one. And we say okay. All right. Now, if you're not absolutely sure whether this thing looks correct or not, what you can do while you're here, well, let's first of all save this. You can go to the display tab, see that display right there? And under, let me hide actually, yeah, that's fine. Under the display preferences, right now it says beam rendering style is none. Let's put it on the solid, and you can see it. If this is not correct, then your orientation point is not correct, and you have to fix it. Okay, so anyway, this is exactly what I want. Fine. All right. Oh, incidentally, if you want to see the orientation axis, you click on this box. This thing lights up. It's kind of hard to see here. If you change the size of the symbol, you can see that. So Axis 1 going to the right, axis 2 going up. So let's check that whether it agrees with what I have here. Axis 1 going to the right. Remember, this was a typo. Yep. Axis 2 going up, and axis 3 is really along the beam. So it agrees with this drawing. So we seem to be okay. All right. Now, anything you don't like, you can hide it from here. For example, back to none. And then we let me say that don't even show me these orientation axes. Okay, fine. Let's close that. All right. Now, what I'm going to do is I will first of all update everything. All right. Uh, Now this is where we have to specify our connections, the rigid connection, the stuff we have to define here, and the lumped masses we have to define here. One of them is on the connection, the other one is on the abstraction. So let me do the rigid connection first. Connections, and here is the rigid connection. You click on it. And read this thing carefully. It says that support one. Remember, I'm doing the bottom floor. Okay, so this is the uh, uh, so this is the support, okay? And I need, this is the one that I want to make is rigid basically. And then I need a reference point. The reference point by default says ground, but I want to create it. It says create a point. It says, well, where do you want to create it? I select this geometry right there. You see that? That's what this thing says. Select this. Okay, how do we want to make that? Well, I want to define it on a curve. Well, it says, where's the curve? The curve is right here. And how do you want to do that? Ratio of the curve length, and I make it 0.5. All right, halfway in between, we say, okay. Created a point right there, and this is the point. This is the point that I want to select, not the ground. This is the point that I want to select. Okay. And that's fine. It's a kinematic coupling. So we say fine. And I repeat this thing for the one on the top. So another rigid connection. This is the support. Put the cursor there, right click, create a point, basically. That is the geometry that I want to create a point on. And I want to do it with on a curve, that curve. And halfway between, which is exactly what I did before. You say, okay, now it is selected right there. This is the one, number 9. The other one should have been number 8, I suppose. Let's go check it. We say, okay, here, no problem. But if you're not sure, we can always go check. It's under connection here. The first one. You know what I'm going to do is I'm going to select that point number 8. Let's actually find out something, because it said vertex. It didn't literally pick number 8. So if I put the cursor here, notice that it does pick a point 8. If you feel more comfortable, you can select this. Okay, it says 0.8. Let me see if I can do that. I don't want two entities. Remove all, and this is going to be there. Okay. Now, the other one would have been fine too, but because that vertex that I picked, it was actually 0.8. We say fine. Good. Now we're going to we're going to place our lumped masses at these two locations. So you click on by the way, we have to tie these things. We can do that now, or we can do that later. Let me try to tie it. Okay. So if you go back to that slide, you see what I did. That's exactly what I'm getting at now. Okay, I'm doing the first floor. So for the green, I select that guy. And for the purple, I select the things that are connected to, and they're going to be tied together, tied to that horizontal first floor. That guy and this guy. Okay, now notice that I did not check this. And you will get error message. We have to come back and check this and put a dummy tolerance here. You say, okay, no problem there. All right, let's do another one. High. This time it's this floor, And for the purple one, I select that fellow and notice that once again, this is not checked. So what I'm doing now is basically these steps. Okay? So, all right. Good. Do a quick save. All right, we will now go and place the lump masses there. So under the abstraction, here is a point inertia or lump mass. You select it. For the support, let me select point 8. Let me see, I can do it from here. Point 8 is that location. And this, based on the information that's given to you, was, let me see, 136. The other one was 66. 136, this is the correct unit. I changed it in my units. All right, now if you see it too big, there's a reason. I can fix that. Let me actually fix it for you now so that you don't get confused. Click on the display, click on the display tab. This is the size of the icon. There we are. And then we close it. All right. Let's do another lump mass. So under abstraction, another one, and that's going to be 0.9. And this one was 66. And we say, okay, good. Now, we're pretty much done here. Okay, so let's actually update everything. All right, and save. Now we're going to go apply our boundary conditions. Okay, so we have to go to structural scenario creation. We are done with the meshing and these little things that we had to do, and select the finite element model that we created. Good. Okay, so first of all, under the procedures, you click on the procedures tab here because notice that there's a red exclamation mark, says no procedure exists. So you click on the procedure and we're going to do a frequency step. 10 frequencies, that's fine. Now boundary conditions. We're going to clamp this. First of all, let's select all of these planes, all of these lines, and say you cannot move in the direction X and you cannot rotate about Y and Z. Essentially, make it a two-dimensional problem. So we can do that right here. 1, 2, all of them. We say you guys cannot move in the direction X, which is perpendicular to this, and rotation Y and Z are fixed. Okay, so that essentially that makes it a two-dimensional problem. Then I'm going to select these corner points at the bottom and say you're clamped. Okay, so all I have to do for clamp, so let's see that boundary conditions. You can clamp it if you want, but I prefer to use these fixed displacement. Now, make sure you do not put it on these points. Let me hide the point. These are the points that I use for creating my geometry. I'm going to hide it either from here or the tree. And all you need to do is to say, you can move in the direction, uh, well, so that we don't think too much, just clap. For example, we know it's not going to move in direction X. We know that it's not going to rotate about Y and Z because it's on those edges that I pick. But anyway, we don't want to think that much. So the supports are this point and that point. That means clamped. Say okay. All right. It looks like we are good. So let me save everything. And one more thing I want to check is that notice that when I created my scenario, immediately it created this branch which allows me to see what kind of element I'm using. If you double click on this, it says B32. Now, if I had used two noded element when I was meshing, that would be B31 and two other one B31H, etc. But because I said in the meshing use three noded element, then it's B32 that I want. So it is pretty much exactly what that gentleman is using in YouTube. All right, this is all saved, and let's go ahead and run it and watch for the errors. So We're going to go to simulate, click on the model and scenario check. That should be okay. Now this is where we're going to run into problem. Simulation check. Say okay. All right. So it gives you this error message, and it really doesn't mean much. Okay. So let's wait for it to finish. Okay. We can go to the diagnostic file. It gives you a little bit more information, but once again, it's not easy to find out what is going on here. So that being the case, let me go ahead back to the mesh, which was here. Double click on this, double clicking on that. Notice that we did these things. Let me show you what I'm referring you. We did these things in the tie section. You go to the tie section. Okay, so go to the tie, open it up, expand, expand, right there, double click, check that box, and put in anything but 0.001. And as I said, this is not obvious why that was the solution. But if you look at the diagnostic file, and stare at it for a while, and you see that it may have something to do with this. Not a guarantee. Double click, specify position, 0.001. You say OK. Let me save. All I did was to check that box and put it non-zero tolerance. Okay. And then back to the scenario. Model is going to go through, no problem. The simulation check, which crashed at that point. Let's see what happens now. If it goes through, no error messages, that's a good sign. There are some warnings that you may want to check and find out what the issue may be, but warnings are okay. Good, didn't crash. And finally, run it, simulate it, run it. It's going to extract 10 frequencies, and we have 6 of them from the YouTube, I think, or maybe 4 of them. The first 2 are rigid body modes, which you can ignore. Yeah, it's going through. Extracting result, that means it actually worked. And we're going to look at the results right there. So these numbers, 1.77, 5.093, etc., are comparable to 1.8, 5.22, etc. So you get the picture. This was not a hard problem because it's similar to, in principle, it was similar to tutorial 1, 2, and 3, but in particular, tutorial 3, where I used actually tied connections, but you can see that there are some subtle issues that you have to pay attention to, otherwise it does not work. Good luck.